Imagine staring into the night sky, where every tiny point of light represents a star, a galaxy, or even an entire cosmic mystery waiting to be unraveled. Now picture something far more fleeting and powerful, a flash of energy so intense it outshines entire galaxies in seconds, then vanishes without a trace. These are gamma-ray bursts, the universe's most violent explosions, and some of them come from the very edge of time itself. What if I told you that scientists have detected bursts so distant, their light has traveled for billions of years just to reach us? These aren't just cosmic fireworks, they're messages from the early universe, carrying secrets about how everything began. Gamma-ray bursts are like cosmic fingerprints, each one revealing clues about the conditions that shaped our universe. The most distant ones, spotted at the farthest reaches of space, are more than just scientific curiosities, they're time capsules. When we observe them, we're peering back to a time when the universe was young, chaotic, and utterly unrecognizable. The energy released in these bursts is almost incomprehensible, equivalent to converting the entire mass of our sun into pure energy in just a few seconds. And yet, despite their mind-bending power, they were only discovered by accident in the late 1960s, when military satellites picked up strange bursts of radiation that had nothing to do with Earth. So what makes these distant gamma-ray bursts so extraordinary? For starters, they challenge everything we thought we knew about the early universe. Some of them originate from the deaths of massive stars, while others might come from collisions of unimaginably dense objects. But the real magic lies in their distance. The farther away they are, the further back in time we're looking. The most distant bursts ever detected let us witness the universe as it was just a few 100 million years after the Big Bang, a time when the first stars were flickering to life. Over the next few minutes, we're going to uncover 30 astonishing facts about these cosmic beacons, facts that will make you rethink the scale of the universe, the forces that govern it, and our place within it. Buckle up, because we're about to journey to the edge of existence itself. At the heart of gamma-ray bursts lies a staggering paradox. They are both unimaginably brief and unbelievably powerful. Picture the sun, a constant presence in our sky, radiating energy steadily for billions of years. Now, imagine compressing all that energy into a single flash lasting just a few seconds. That's the raw, explosive force of a gamma-ray burst. These cosmic detonations are the universe's most luminous fireworks, outshining entire galaxies in the blink of an eye. They erupt without warning, flooding space with high-energy gamma rays, light so intense it can pierce through cosmic dust and gas like a beacon cutting through fog. What triggers such extreme violence? Most gamma-ray bursts fall into two categories. The first comes from the death throes of massive stars far larger than our sun. When these giants collapse, they don't go quietly. Their cores implode into black holes or neutron stars, while their outer layers are blasted outward in a hyper-energetic jet moving at nearly the speed of light. If that jet happens to be pointed toward Earth, we witness a gamma-ray burst bright enough to be seen across the observable universe. The second type arises from collisions between ultra-dense stellar remnants like neutron stars. When these objects spiral into each other, they unleash gravitational waves and a torrent of gamma radiation, a celestial demolition derby with consequences visible billions of light-years away. The fleeting nature of these bursts makes them elusive prey for astronomers. Some last mere milliseconds, barely enough time to register their existence before vanishing forever. Others might linger for minutes, offering a slightly longer window to study their secrets. But no matter their duration, one thing is certain: gamma-ray bursts are the ultimate cosmic powerhouses, releasing more energy in seconds than our sun will emit in its entire lifetime. And the most distant bursts, they're not just energetic, they're time machines carrying echoes of an era when the universe was raw, untamed, and teeming with the first generations of stars. The story of gamma-ray bursts begins not with astronomers peering through telescopes, but with Cold War-era satellites designed to watch for nuclear explosions. In the late 1960s, American military satellites named Vela, originally launched to monitor compliance with nuclear test ban treaties, started picking up strange bursts of gamma radiation. These weren't the telltale signatures of secret atomic tests. They came from deep space, appearing at random intervals from all directions. Scientists were baffled. At first, some suspected Soviet space weapons or exotic physics experiments gone wrong. Others thought they might be solar flares or some unknown phenomenon within our own galaxy. It took years of painstaking analysis to realize these flashes were something far more extraordinary: cosmic explosions happening billions of light years away. The turning point came in 1973 when researchers at Los Alamos National Laboratory finally connected the dots. By carefully comparing data from multiple Vela satellites, they proved the bursts originated far beyond Earth, even beyond our Milky Way. Imagine their shock. These weren't just distant events. They were the brightest explosions in the universe since the Big Bang itself, yet so faint when they reached Earth that only sensitive military instruments could detect them. What makes this discovery so remarkable is how perfectly it captures the serendipity of science. These satellites weren't built to study the cosmos. They were looking down at Earth, not up at the stars. Yet in their hunt for human-made explosions, they stumbled upon something infinitely more powerful. The early data was so puzzling that some scientists initially dismissed it as instrument noise or classified the findings entirely, fearing they might reveal satellite capabilities during the tense Cold War era. It wasn't until after declassification that astronomers realized they'd been handed an entirely new window into the universe's most violent events, one that would rewrite textbooks and challenge our understanding of cosmic extremes. Today, we know these bursts are like cosmic lightning, unpredictable, blindingly bright, and carrying unimaginable energy. But back then, their discovery was like finding fingerprints of giants in the dark. The Vela satellites couldn't pinpoint exact locations or distances. They could only whisper that something extraordinary was happening in the void. It would take decades of technological advancement and a new generation of space telescopes to unravel the true nature of these bursts. Yet even now, those first mysterious signals remain a testament to how much of the universe's drama plays out in wavelengths invisible to human eyes, waiting for the right moment and the right tool to reveal its secrets. Gamma-ray bursts aren't just one-size-fits-all explosions. They come in two distinct flavors, each with its own cosmic recipe for chaos. The first, known as short gamma-ray bursts, pack their entire fury into less than 2 seconds. These fleeting but catastrophic events are the universe's way of ending a stellar heavyweight bout when two neutron stars, the dense remnants of dead stars, finally spiral into each other in a violent merger. Picture two city-sized objects, each so dense that a teaspoon of their material would weigh 1 billion tons, colliding with enough force to ripple spacetime itself. The resulting explosion doesn't just produce gamma rays, it's also a factory for heavy elements like gold and platinum, scattering them across the cosmos in a glittering aftermath. Then there are the long gamma-ray bursts, the marathon runners of cosmic destruction. These can blaze for minutes, sometimes even hours, and they trace back to the deaths of the universe's most massive stars. When a star dozens of times heavier than our Sun exhausts its fuel, its core collapses into a black hole while the outer layers are ejected in ultra-relativistic jets. These jets, moving at nearly the speed of light, punch through the star's remaining material and erupt into space as a gamma-ray burst so bright it can outshine a galaxy. What makes long bursts especially fascinating is their connection to supernova. The dying star's outer layers often explode in a spectacular display days or weeks after the initial gamma-ray flash, leaving behind a telltale glow that helps astronomers confirm their origin. So why do the most distant gamma-ray bursts we detect tend to be long ones? It's a matter of cosmic timing. In the early universe, stars were born bigger and burned brighter, with lifespans measured in mere millions of years rather than billions. These titanic stars were perfect candidates for the kind of core collapse explosions that produce long bursts. Short bursts, on the other hand, require neutron star mergers, a process that can take billions of years to unfold as two dead stars gradually lose energy and spiral together. By the time the universe was old enough for these mergers to become common, the era of the gigantic, fast-living stars was long over. That's why when we peer to the edge of the observable universe, we're seeing a time when long bursts dominated the cosmic stage, a window into an age of stellar giants and their spectacular, fiery demises. In 2009, astronomers witnessed a flash of gamma rays so ancient it defied comprehension. The light from GRB 090423 had been traveling toward us for 13 billion years, a journey spanning almost the entire history of the cosmos itself. When this burst erupted, the universe was a mere infant, just 600 million years old, a time when the first stars were still flickering to life in the cosmic dark. To put that into perspective, this explosion happened so long ago that Earth, the Sun, even our Milky Way galaxy didn't exist yet. By the time its light reached us, the universe had expanded so dramatically that the wavelength of those gamma rays stretched into infrared, a faint whisper from the dawn of time. What makes GRB 090423 so extraordinary isn't just its distance, it's the snapshot it provides of a universe in transition. Back then, space was a murky soup of hydrogen gas, slowly being carved apart by the ultraviolet glare of the first stars. This gamma-ray burst acted like a cosmic lighthouse, piercing through that primordial fog and giving scientists a rare glimpse into the era known as reionization, when light began to sculpt the universe as we know it. The fact that we detected it at all is a testament to modern astronomy's power. The Swift satellite, designed to catch these fleeting bursts, spotted it in just 10 seconds of activity before it vanished forever. Yet the real magic lies in what followed. As telescopes around the world swung into action, they captured something unprecedented: the afterglow of the burst shifting redder and redder as the universe's expansion stretched its light like taffy. That redshift measurement, a staggering 8.2, confirmed GRB 090423 as the most distant object ever observed at the time. It held that record for years, a beacon from the cosmic dark ages that challenged our understanding of how quickly stars and the black holes that power such bursts could form after the Big Bang. Today, even more distant bursts have been found, but this one remains a landmark, a reminder that the universe's most violent explosions are also its most eloquent storytellers, carrying tales from epochs we can only dream of witnessing firsthand. Measuring the mind-bending distances to gamma-ray bursts hinges on a cosmic quirk: the stretching of light itself. As the universe expands, it tugs on light waves traveling through space, elongating them like a slinky being pulled apart. This phenomenon, called redshift, transforms the once fierce gamma rays into longer, redder wavelengths by the time they reach us. Astronomers quantify this shift with a simple letter Z, and the higher the Z value, the farther the burst lies in both space and time. A gamma ray burst with a redshift of 1 means its light has doubled in wavelength during its journey, placing it roughly 10 billion light-years away. But some bursts shatter even that scale, with redshifts above 8 or 9, catapulting us back to when the universe was less than 5% of its current age. Pinpointing these distances isn't just about catching the initial flash, it's the afterglow that holds the key. Hours or days after the gamma rays fade, telescopes can still detect lingering light across X-ray, optical, and infrared wavelengths. This afterglow acts like a cosmic breadcrumb trail, leading astronomers to the burst's host galaxy. By splitting this light into a spectrum, a rainbow of wavelengths laced with absorption lines, scientists can read the chemical fingerprints of intervening gas clouds. Each line corresponds to elements like hydrogen or iron, but they're shifted toward the red end of the spectrum compared to their positions in labs on Earth. That shift reveals the exact stretch factor, giving us the burst's redshift with surgical precision. Here's where things get even more fascinating. The most distant bursts often show spectral lines from neutral hydrogen, a relic of the early universe before starlight ionized the cosmos. These lines aren't just distance markers, they're snapshots of the universe's teenage years when it was transitioning from a dark, opaque fog to the transparent expanse we know today. Without redshift measurements, gamma-ray bursts would just be dazzling cosmic anomalies. With them, they become time machines, letting us calibrate the expansion history of the universe itself. Every high-Z burst is a checkmark in our cosmic ledger, testing whether our models of space-time hold up under extreme conditions. And so far, these distant explosions keep confirming while occasionally challenging our understanding of how the universe grew from a fiery birth to the structured cosmos we inhabit today. Detecting gamma-ray bursts is like trying to photograph lightning in a pitch-black sky. You never know where or when the next flash will appear. That's where NASA's Swift and Fermi satellites come in, serving as the universe's lightning rods. Swift, launched in 2004, is the ultimate cosmic watchdog, equipped with a nimble design that lets it swivel toward a burst within seconds of detection. Imagine a telescope that can spin 180 degrees in less than a minute, locking onto fading afterglows before they vanish, its secret weapon. A trio of instruments working in harmony, the Burst Alert telescope spots the initial explosion, while X-ray and ultraviolet/optical telescopes dissect the aftermath with surgical precision. Fermi, on the other hand, is the heavyweight champion of high-energy astronomy. Since its launch in 2008, its large-area telescope has been scanning the sky for gamma rays with energies 1,000,000 times greater than visible light. But Fermi's real genius lies in its timing. It can pinpoint bursts so fast that its data often reaches astronomers before Swift even finishes turning. Together, these satellites form a tag team unmatched in cosmic surveillance. When one detects a burst, it instantly beams coordinates to observatories worldwide, triggering a global race to capture every possible wavelength of light from radio waves to gamma rays. What makes this duo truly revolutionary is their ability to catch bursts in the act. Before Swift and Fermi, astronomers were like detectives arriving at a crime scene after the suspect had fled. Now they're witnessing the explosions unfold in real time, watching as jets of particles slam into surrounding gas at near light speed, creating shock waves that glow across the electromagnetic spectrum. This rapid response network has transformed gamma-ray bursts from cosmic curiosities into precision tools for probing the universe's most extreme environments. The satellite's alerts have led to some of the most groundbreaking discoveries in modern astrophysics, like catching the first gravitational waves from colliding neutron stars alongside their gamma-ray flash. Without these tireless sentinels in orbit, we'd be missing half the story, like trying to understand thunderstorms by only listening for distant thunder. Every burst they catch is another piece of the puzzle, helping us decode how black holes form, how heavy elements are forged, and how the universe itself grew from a sea of primordial plasma to the structured cosmos we see today. Gamma-ray bursts don't just light up the cosmos, they illuminate history itself. When we detect a burst from the edge of the observable universe, we're not just seeing an explosion, we're intercepting a message from a time when galaxies were still taking shape. The most distant bursts act like cosmic time capsules, preserving conditions from an era when the universe was a mere fraction of its current age. Take GRB 090423, for example. Its light traveled 13 billion years to reach us, carrying information about the chemical makeup of the early cosmos back when heavy elements like carbon or oxygen barely existed, and space was filled with pristine hydrogen and helium from the Big Bang. What makes these bursts uniquely powerful as time machines is their ability to cut through the fog of the early universe. During the cosmic dark ages, before stars and galaxies fully formed, space was filled with neutral hydrogen gas that absorbed ultraviolet light, making it nearly impossible to see through. But gamma rays, they blast straight through this haze like a searchlight, allowing us to peer into epochs otherwise hidden from view. By analyzing how the afterglow of these bursts interacts with intervening gas clouds, astronomers can map the distribution of matter across billions of light years, reconstructing the universe's growth spurt from infancy to maturity. The real breakthrough comes when we compare bursts from different distances. A gamma ray burst from 10 billion years ago might show us a universe already rich with galaxies, while one from 13 billion years ago reveals a cosmos still assembling its first structures. It's like flipping through a photo album of the universe's childhood. Each burst captures a different developmental stage. Some even bear traces of the very first stars, known as population Roman III stars, which were massive, short-lived, and forged the initial heavy elements that seeded future generations of stars and planets. But the surprises don't stop there. Distant bursts also help us test one of cosmology's greatest mysteries: how fast the universe is expanding. By measuring the brightness and redshift of bursts, scientists can calibrate the cosmic distance ladder, checking whether our models of dark energy and universal expansion hold up across time. Some studies suggest that the most ancient bursts might even hint at variations in fundamental constants, like the speed of light or the strength of gravity over cosmic history. In essence, every distant gamma-ray burst is a Rosetta Stone for the early universe. They don't just tell us about the explosions themselves, they reveal the backdrop against which these cataclysms occurred. Whether it's tracing the ionization of hydrogen by the first starlight or uncovering the growth of cosmic structure, these fleeting flashes give us front-row seats to the universe's most formative chapters, no time machine required. The sheer energy unleashed in a single gamma-ray burst defies human intuition. We simply lack any earthly reference point for such cosmic violence. Picture the sun, a nuclear furnace that has bathed our solar system in light for 4.6 billion years. Now imagine condensing every photon, every solar flare, every speck of energy our star will ever produce into just 10 seconds. That's the scale we're talking about with a typical gamma-ray burst. In those fleeting moments, a single burst can radiate as much energy as the sun will emit across its entire 10 billion-year lifespan. To grasp this unfathomable output, consider the most destructive forces humans have ever harnessed. The largest nuclear bomb ever detonated, Tsar Bomba, released energy equivalent to 50 megatons of TNT, enough to level cities and carve craters into the Earth's crust. A gamma-ray burst unleashes the energy of 1 trillion such bombs in mere seconds. If one occurred within a few thousand light-years of Earth, the intensity of its gamma rays would strip away our ozone layer, triggering mass extinctions. Thankfully, the nearest known bursts are millions of light-years away, but their distant fury still serves as a humbling reminder of nature's raw power. What fuels such staggering energy release? The answer lies in relativistic jets, twin beams of particles and radiation shooting outward at 99.99% the speed of light. These jets funnel the gravitational energy of a collapsing star or colliding neutron stars into narrow cones, concentrating their output like a cosmic blowtorch. The physics behind them taps into Einstein's famous equation, E equals mc squared, converting vast amounts of mass directly into pure energy. In a long gamma-ray burst, for instance, the collapsing core of a massive star might convert solar masses worth of material into gamma rays in minutes, a process so efficient it makes our sun's fusion-powered glow look like a candle flicker. The afterglow of these bursts adds another layer of awe. As the jets plow into surrounding gas, they create shock waves that emit X-rays, visible light, and radio waves for weeks or months. This lingering glow often outshines entire galaxies, a testament to the energy reservoirs these events tap into. Scientists estimate that a single gamma-ray burst can release up to 10 to the 44 joules of energy, roughly the same as converting the entire mass of Jupiter into pure radiation. That's not just a stellar-scale explosion, it's a fundamental reshaping of spacetime itself, carved into the universe's history by forces we're only beginning to comprehend. The moment a gamma-ray burst fades from view, the real detective work begins, because these explosions leave behind luminous echoes across the electromagnetic spectrum, like cosmic breadcrumbs leading scientists to their secrets. These afterglows aren't just fading remnants, they're vibrant, multi-wavelength fingerprints that reveal everything from the burst's energy to the structure of its surroundings. X-rays, the first to emerge, act like a high-energy autopsy, showing how the blast wave plows through interstellar gas at near light speeds. Then come the optical and infrared afterglows, glowing like embers in a cosmic campfire, their colors shifting as expanding space stretches their wavelengths over days or weeks. Finally, radio waves persist the longest, sometimes for months, tracing the shock waves as they slow and spread into the interstellar medium. What makes these afterglows so valuable is how they transform a fleeting flash into a prolonged cosmic laboratory. Take X-ray afterglows, for example. The Chandra and XMM Newton telescopes have caught them flickering in intricate patterns, revealing details about the central engine, often a newborn black hole or magnetar, still pumping energy into the jet long after the initial explosion fades. Optical afterglows captured by instruments like the Hubble or ground-based observatories do something even more remarkable. They light up the burst's host galaxy, allowing astronomers to measure its distance, composition, and even the density of gas between us and the explosion. It's like turning a flashlight on in a dark forest. Suddenly, everything along its path becomes visible, but the real showstoppers are the radio afterglows. Unlike higher energy light, radio waves can pierce through cosmic dust that would otherwise obscure our view. The Very Large Array in New Mexico has tracked these signals as they bounce off interstellar clouds, creating interference patterns that map the burst's environment in 3 dimensions. Some afterglows even show bizarre rebrightening episodes, suggesting the jet might be plowing into dense shells of material ejected by the progenitor star before its death. These delayed echoes give us a play-by-play of the star's final, turbulent years. Perhaps the most groundbreaking insight comes from comparing afterglows across wavelengths. A burst's X-ray afterglow might reveal a sharply collimated jet, while its radio glow shows wider, slower-moving material swept up in the blast. This mismatch helped solve a long-standing puzzle: why some bursts appear under energetic. The answer: we're often seeing these jets off-axis, like staring at a flashlight beam from the side rather than head-on. By studying afterglows from every angle, scientists have pieced together a unified model where the same basic physics, ultra-relativistic jets interacting with their surroundings, can explain bursts of all durations and intensities. These luminous echoes do more than just illuminate the bursts themselves. They act as probes of the cosmos at large. The way an afterglow dims over time encodes information about the density and magnetic fields of intergalactic space, while its spectrum can reveal absorption lines from gas clouds billions of light-years away. It's as if each burst paints a cross-section of the universe along our line of sight, turning a single catastrophic event into a tool for mapping the cosmos. Without afterglows, gamma-ray bursts would remain enigmatic flashes. With them, they become Rosetta Stones, translating the universe's most violent language into something we can finally begin to understand. The explosive demise of a massive star isn't always a quiet fade into darkness. Sometimes, it's a spectacular, universe-shaking finale that lights up the cosmos. Long gamma-ray bursts serve as the death cries of these stellar giants, announcing their collapse into oblivion with a brilliance that outshines galaxies. But these aren't just any stars meeting their end, they're cosmic powerhouses, dozens of times more massive than our Sun, spinning so fast their cores resemble whirlpools of nuclear fire. When such a star exhausts its fuel, gravity wins the final battle, and what happens next redefines the word cataclysmic. At the heart of this destruction lies a phenomenon called a hypernova, a supernova on steroids. Unlike ordinary supernova, which leave behind neutron stars or quiet black holes, hypernova channel their energy into narrow, ultra-fast jets that punch through the star's outer layers like cosmic lasers. This happens because the progenitor star isn't just massive, it's also rapidly rotating, creating a swirling maelstrom of plasma around its core. As the core collapses, this rotation gets amplified, forming a dense, spinning disk of material around the newborn black hole. The disk acts like a particle accelerator, funneling jets of matter and radiation along the star's rotation axis at nearly light speed. If Earth happens to lie in the path of one of these jets, we witness the full fury of a gamma-ray burst. The physics behind these jets is as breathtaking as their effects. Magnetic fields, twisted tighter than a tornado by the star's spin, become cosmic slingshots, launching material outward with forces that dwarf anything in our solar system. Temperatures in these jets reach trillions of degrees, hot enough to briefly recreate conditions from the Big Bang itself. Meanwhile, the black hole at the center, often several times the Sun's mass, continues to feed, swallowing surrounding gas and driving the jets for minutes or even hours. This sustained energy release is why long gamma-ray bursts can outlast their short-duration cousins, which arise from neutron star mergers rather than stellar collapses. What's truly mind-bending is how much we've learned from these explosions. By studying hypernova remnants and their associated gamma-ray bursts, astronomers have pieced together a stellar life cycle far more dramatic than anyone imagined a century ago. These events don't just destroy stars, they seed the cosmos with heavy elements like gold, platinum, and uranium, forged in the heart of the explosion or in the jets themselves. The afterglows of long bursts often reveal telltale signatures of these elements, confirming hypernova as cosmic alchemists on a scale dwarfing anything in human experience. Yet for all their destructive power, hypernova and their gamma-ray bursts play a paradoxical role in the universe. They're both annihilators and creators. The same jets that tear stars apart also clear surrounding gas clouds, triggering new star formation in their wake. The heavy elements they scatter become building blocks for future planets and perhaps life. In a very real sense, we owe our existence to generations of such violent stellar deaths, each one a reminder that even in the cosmos, destruction and creation are two sides of the same coin. The next time you look up at the night sky, remember some of those distant points of light may one day end not with a whimper, but with a gamma-ray burst that echoes across the universe. The universe may seem vast and indifferent, but every so often, it reminds us of just how fragile our existence truly is, and few cosmic events drive that point home like the nightmare scenario of a nearby gamma-ray burst. Picture this, a star within our own galaxy, perhaps just a few thousand light-years away, collapses in a hypernova explosion so powerful its gamma-ray jet sweeps across space like a celestial scythe. Within seconds, Earth's upper atmosphere is bombarded with enough high-energy radiation to strip away our ozone layer, leaving the planet's surface exposed to the Sun's unfiltered ultraviolet fury. Within weeks, ecosystems collapse as radiation mutates DNA, crops fail, and food chains unravel. Scientists estimate that a gamma-ray burst striking Earth from even 6,000 light-years away could trigger mass extinctions rivaling the asteroid impact that wiped out the dinosaurs. But here's the chilling twist: it's happened before. Geological evidence hints that a gamma-ray burst or similar event may have contributed to the Ordovician extinction 450 million years ago, when up to 85% of marine species vanished. Sedimentary rock layers from that period show spikes in radioactive isotopes, while fossil records reveal abrupt drops in biodiversity consistent with sudden, intense radiation exposure. The culprit, a nearby hypernova or neutron star collision, its gamma-ray jet angled just right to graze our planet. Today, remnants of such events linger in our galaxy, like WR104, a massive star 8,000 light-years away that's primed to explode as a gamma-ray burst. If its poles align with Earth when it goes, we'd witness a light show brighter than the full moon, followed by a silent, invisible catastrophe. Thankfully, the odds are overwhelmingly in our favor. Statistically, a galaxy like the Milky Way experiences a gamma-ray burst capable of threatening Earth only once every few 100 million years. Most bursts fire their jets in narrow cones, meaning even a nearby explosion would likely miss us entirely. Plus, our solar system's position far from the crowded, star-forming regions where massive stars congregate reduces the risk further. Modern telescopes like Swift and Fermi serve as early warning systems, monitoring the sky for telltale gamma-ray flashes. If a dangerous burst ever did occur, we'd detect its light years before the damaging radiation arrived, giving humanity time to, well, brace for impact. So while the cosmic dice could theoretically roll against us, the universe's sheer size is our best shield. Gamma-ray bursts are terrifying in their power, but they're also vanishingly rare, a reminder that space's most violent spectacles are best admired from a very, very safe distance. Not every gamma-ray burst puts on a visible light show. Some explode into the cosmic void and leave behind nothing but darkness. These are the enigmatic, dark gamma-ray bursts, events that defy expectations by producing powerful gamma-ray flashes but no detectable optical afterglow. It's like hearing thunder without seeing lightning, a cosmic puzzle that has left astronomers scratching their heads for years. While most bursts paint the sky with fading embers of X-rays, visible light, and radio waves, dark GRBs vanish without a trace, their secrets locked away behind veils of dust or encoded in the exotic environments of their host galaxies. The leading theory points to cosmic dust as the culprit. Imagine a gamma-ray burst erupting inside a dense, star-forming region shrouded in thick clouds of interstellar soot. The initial gamma rays blast through unimpeded. They're too energetic to be blocked, but the lower energy optical light from the afterglow gets absorbed and scattered like headlights dimmed by fog. Supporting this idea, many dark bursts reveal faint infrared glows when studied with telescopes like Spitzer or JWST, hinting that dust is indeed re-radiating the absorbed energy at longer wavelengths. Some of these bursts might originate in galaxies vastly different from our Milky Way, places where dust is so pervasive it chokes out starlight entirely, rendering afterglows invisible to conventional telescopes. But dust isn't the only explanation. Some dark GRBs could be the cosmic equivalent of sniper shots, jets angled so far away from Earth that we only catch a glancing blow of gamma rays, missing the brighter afterglow emission that beams outward in narrower cones. Others might originate at such extreme distances that their optical light gets stretched into the infrared by cosmic expansion, slipping past the detection limits of optical instruments. There's even speculation that a fraction of these bursts could herald entirely new classes of cosmic explosions, perhaps involving exotic objects like quark stars or primordial black holes. Unraveling this mystery requires more than luck, it demands innovation. Astronomers now use rapid response systems to scan the skies for dark bursts within minutes of detection, hoping to catch any whisper of an afterglow before it fades. Radio observatories play a crucial role, as radio waves can pierce through dust that blinds optical telescopes. Meanwhile, gravitational wave detectors like LIGO and Virgo listen for subtle ripples in spacetime that might accompany these events, offering clues about their origins. Every dark burst studied peels back another layer of the cosmic onion, revealing how stellar deaths vary across different galactic environments. What makes dark GRBs so compelling isn't just their elusiveness, it's what they imply about the universe's unseen corners. If a significant fraction of gamma-ray bursts are going dark, we might be missing a silent majority of cosmic explosions, their stories untold because they hide in dusty or distant realms. Each one challenges our assumptions, reminding us that the universe's most violent events often prefer to operate in the shadows. The hunt for answers continues, driven by the tantalizing possibility that within these enigmatic bursts lie clues to galaxies and phenomena we've yet to even imagine. Hidden within the fiery chaos of a neutron-star collision lies one of the universe's most astonishing alchemical processes, the birth of gold, platinum, and other precious metals we treasure here on Earth. When two neutron stars spiral together in a cataclysm powerful enough to produce a short gamma-ray burst, they don't just unleash a torrent of radiation, they become cosmic forges, synthesizing elements heavier than iron in a heartbeat. This rapid neutron capture process, or R process, is nature's way of building atomic nuclei dense with neutrons, a feat impossible under the gentler conditions inside ordinary stars. Picture the moment of impact: two ultra-dense stellar remnants, each packing a sun's worth of mass into a city-sized sphere, slammed together at relativistic speeds. The outer layers of these neutron stars are torn apart, ejecting neutron-rich material into space at temperatures exceeding 1 billion degrees. In this soup of free neutrons and atomic nuclei, something extraordinary happens. Atomic nuclei snatch up neutrons like sponges soaking up water, growing heavier and heavier in fractions of a second. Before the resulting explosion can blast this material apart, radioactive decay stabilizes these overstuffed nuclei, transmuting them into stable elements like gold, platinum, and uranium. A single merger can produce hundreds of Earth masses worth of these heavy elements, scattering them across interstellar space in glowing, radioactive clouds. The evidence for this cosmic goldsmithing became undeniable in 2017, when the LIGO and Virgo detectors caught gravitational waves from neutron star merger GW170817. Telescopes worldwide swung into action, capturing not just the gamma-ray burst but also the kilonova, a telltale glow powered by the radioactive decay of freshly minted R-process elements. Spectroscopic analysis revealed signatures of cesium, tellurium, and gold in the expanding debris, confirming what theorists had long suspected. These mergers aren't just spectacular light shows, they're the primary source of the heaviest elements in the universe. Here's the mind-blowing part. The gold in your jewelry or the platinum in a catalytic converter likely began its existence in a neutron star collision billions of years ago. These elements, too heavy to form in supernova, were forged in the heart of a gamma-ray burst's aftermath, then scattered across the galaxy until some fraction found its way into the molecular cloud that birthed our solar system. Every time you hold a piece of gold, you're holding stardust, but not just any stardust. This is debris from one of the universe's most violent and exquisite transformations, a relic of neutron stars that ceased to exist before Earth even formed. The implications stretch far beyond bling. Without these mergers, the periodic table would stop at iron, leaving planets devoid of uranium for nuclear reactors, iodine for medical imaging, or even lead for radiation shielding. Gamma-ray bursts, in their role as heavy element factories, didn't just enrich the cosmos, they made possible the chemistry of life as we know it. Future studies aim to quantify exactly how much gold a single merger produces, with estimates suggesting anywhere from 3 to 100 times the mass of Earth's oceans. That's enough to gild every planet in the Milky Way. If only we could mine it. For now, we'll have to settle for the knowledge that the universe's most dazzling explosions are also its most generous artisans, turning the ashes of dead stars into treasures that outlast galaxies. Within the blistering jets of a gamma-ray burst, particles reach speeds so extreme they make Earth's most powerful particle accelerators look like toys. These cosmic explosions don't just release energy, They act as natural particle colliders, hurling protons and electrons to velocities within a hair's breadth of light itself. The result, cosmic rays with energies dwarfing anything produced in human laboratories, carrying millions of times the punch of particles in the Large Hadron Collider. If our most advanced machines can accelerate protons to the equivalent of a bullet's speed, gamma-ray bursts launch them like interstellar cannonballs, achieving energies so high they defy conventional physics. The secret lies in the burst shockwaves. As the jet plows through surrounding gas, it creates turbulent magnetic fields that act like cosmic pinball machines, slinging particles back and forth until they accumulate mind-bending momentum. Some protons emerge with energies exceeding 10 to the 20 electron volts, enough to make a single subatomic particle carry the kinetic energy of a well-thrown baseball. Detectors like the Pierre Auger Observatory in Argentina have spotted these ultra-high-energy cosmic rays raining down on Earth, their origins traced back to distant galaxies hosting gamma-ray bursts. Unlike the controlled collisions in human-made colliders where particles smash together in precise beams, these natural accelerators operate on a scale so vast they turn entire regions of space into sprawling particle factories. What's truly humbling is how these bursts outperform our technology without even trying. The Large Hadron Collider, a 27-kilometer ring buried beneath Switzerland and France, requires enough electricity to power a small city just to nudge protons close to light speed. A gamma-ray burst achieves far greater energies across light years of space, using nothing but gravity and magnetic fields. Yet there's a crucial difference. While the LHC's collisions are meticulously documented, gamma-ray bursts hurl particles chaotically, leaving scientists to piece together their mechanics from the debris that eventually reaches Earth. These particles don't just break records, they challenge our understanding of physics. At energies this extreme, protons should interact with the cosmic microwave background, losing momentum over intergalactic distances. The fact that we detect them at all suggests gaps in our models, possibly pointing to new physics or exotic cosmic phenomena we've yet to discover. Some theorists even speculate that the highest energy cosmic rays might be signatures of dark matter annihilation or other undiscovered processes lurking within gamma-ray bursts. Next time you hear about a high-energy physics breakthrough, remember, the universe has been running its own particle experiments for billions of years, with gamma-ray bursts as its unrivaled accelerators. They're reminders that for all our ingenuity, nature's extremes still hold secrets no lab on Earth can yet unravel. Among the many cosmic engines capable of powering gamma-ray bursts, few match the sheer intensity of Magnetar's neutron stars with magnetic fields so strong they bend the laws of physics. These stellar remnants pack the mass of a sun into a sphere no wider than Manhattan, but their true power lies in magnetism a quadrillion times fiercer than Earth's. When a magnetar erupts, its magnetic field twists like a coiled spring until it snaps, releasing energy equivalent to 1 billion atomic bombs in a millisecond. Some scientists suspect these catastrophic magnetic quakes could be behind a subset of gamma-ray bursts, particularly those with unusual light curves or prolonged X-ray afterglows that defy explanation by typical black hole models. The smoking gun linking magnetars to bursts emerged from observations of unusual GRBs with plateau phases, periods where their X-ray emissions linger far longer than expected. While most bursts fade rapidly as their central black hole stops feeding, these events show steady glows lasting hours or even days, as if some unseen power source keeps pumping energy into the aftermath. Magnetars fit this profile perfectly. Born from the collapse of massive stars, these spinning magnets can channel their rotational energy into sustained jets via their monstrous magnetic fields, acting like cosmic batteries that refuse to die quietly. One notable example, GRB 080319b, displayed an X-ray plateau so stable it could only be explained by a newborn magnetar stubbornly resisting its own demise. What makes magnetar-powered bursts truly unique is how they distort spacetime itself. Magnetic fields this strong can actually twist the quantum vacuum, creating conditions where light behaves bizarrely, splitting into multiple wavelengths or even birthing particles from empty space. Simulations suggest that when a magnetar's crust fractures under magnetic strain, it triggers starquakes that ripple across its surface, launching relativistic jets laced with polarized gamma rays. This polarization, a telltale alignment of light waves, has been detected in several bursts, offering indirect evidence of magnetar involvement. The European Space Agency's integral satellite even caught one burst with gamma rays so polarized they implied magnetic fields strong enough to shred atoms into subatomic confetti. Yet magnetars remain enigmatic. Some theorists argue they could explain fleeting, millisecond bursts too brief for traditional collapse models, while others propose they're behind mysterious, soft gamma repeaters, cosmic objects that flare repeatedly rather than vanishing after one explosion. The key to unlocking these puzzles lies in next-generation telescopes capable of measuring magnetic field signatures in real time. When NASA's upcoming COSI mission launches in 2027, its gamma-ray polarimeter may finally catch a magnetar in the act of birthing a burst, watching as its magnetic fury sculpts jets visible across the universe. Until then, these ultramagnetic zombies of the cosmos continue to challenge our understanding of how stars die, and how even in death their magnetism can light up the sky. Gamma-ray bursts don't just reshape galaxies, they might hold the answer to one of humanity's oldest questions: are we alone in the universe? The sheer destructive power of these cosmic explosions raises a chilling possibility. What if GRBs act as galactic sterilizers, wiping out potential life across vast regions of space? Imagine a habitable planet teeming with emerging life, only to be bathed in lethal gamma radiation from a burst thousands of light years away. In an instant, complex organisms could be obliterated, their atmospheres stripped of protective ozone, and their surfaces bombarded with enough energy to trigger mass extinctions. This grim scenario isn't science fiction. It's a real constraint scientists call the GRB habitable zone, the regions of a galaxy where life might survive long enough to evolve without being periodically reset by these catastrophic events. The math is sobering. In galaxies with frequent gamma-ray bursts like those in the early universe or today's star-forming regions, the odds of complex life surviving long enough to develop intelligence plummet. Astronomers estimate that in certain galactic neighborhoods, a planet could be hit by a sterilizing burst every few 100 million years, resetting the evolutionary clock before multicellular life gains a foothold. Our own Milky Way, however, sits in a relatively quiet suburban region, with fewer massive stars capable of producing GRBs. Even here, Earth likely experienced near misses over its 4.5 billion-year history. Geological evidence hints that a burst within 6,000 light-years might have triggered the Ordovician extinction 450 million years ago. But there's a twist in this cosmic survival story. Some researchers argue that GRBs might paradoxically enable life by dispersing heavy elements essential for biology, like phosphorus and iodine, across interstellar space. Others propose that civilizations advanced enough to detect incoming bursts could shield themselves, building underground habitats or even deflecting gamma-ray jets with futuristic technology. The most intriguing idea, that gamma-ray bursts might explain the Fermi paradox, the eerie silence of the cosmos despite its vast number of stars. If lethal GRBs are common in certain galaxies, it could mean intelligent life keeps getting wiped out before it can signal its existence. Yet the universe loves balance. While intergalactic regions face higher GRB risks, they also host more metals and organic molecules, the building blocks of life. Outer regions are safer from bursts but starved of these crucial ingredients. This creates a cosmic Goldilocks zone, not just for planets but for entire galaxies. Spiral galaxies like ours, with their mix of quiet suburbs and bustling stellar nurseries, might strike the perfect balance, rare enough bursts to allow life, but frequent enough to seed it with necessary elements. The search for extraterrestrial intelligence now includes a new filter, scanning distant galaxies for GRB rates. A galaxy silent of radio signals but rich in gamma-ray bursts might tell us why we haven't found neighbors, not because life is rare, but because the universe itself is a minefield. Meanwhile, our existence here raises another tantalizing question. Did we luck out in a cosmic survival game, or is life more resilient than we think? Every burst we detect carries two messages: a reminder of how fragile life can be, and a challenge to outlast the universe's most violent explosions. In 2020, astronomers witnessed a cosmic blink and you'll miss it event. GRB 200826a, a gamma-ray burst so fleeting it lasted just 0.65 seconds. To put that into perspective, it took you longer to read this sentence than the entire explosion lasted. At first glance, this ultra-brief burst should have fit neatly into the short category, typically linked to neutron star collisions. But when researchers analyzed its afterglow, they found something bizarre. The fingerprints of a collapsing massive star, the hallmark of a long gamma-ray burst. This cosmic contradiction forced scientists to rethink the very definition of what makes a burst short or long. The discovery turned classification systems upside down. For decades, astronomers used a 2-second rule. Bursts shorter than 2 seconds came from compact object mergers, while longer ones signaled dying stars. GRB 200826 shattered that simplicity. Its light curve revealed a telltale bump days later, the signature of a supernova, something never before seen with a sub-second burst. This suggested the progenitor star collapsed so rapidly that its death scream was cut short, like a candle snuffed out mid-flame. The implications: some massive stars might die with a whimper rather than a bang, producing bursts so brief they masquerade as neutron star mergers. What makes this burst revolutionary isn't just its brevity, it's the window it opened into stellar death's hidden diversity. Simulations now suggest that a star's rotation, magnetic fields, or even internal turbulence could sometimes truncate its collapse into a near-instantaneous event. Imagine a skyscraper demolishing itself not with a dramatic explosion, but with a single, precise implosion, swift, efficient, and eerily quiet. GRB 200826 proved that gamma-ray bursts don't always play by the rules, hinting at an entire spectrum of stellar deaths we're only beginning to catalog. The hunt is now on for more of these boundary-defying bursts. Next-generation telescopes like the Vera Rubin Observatory, with its ability to scan the entire sky nightly, could uncover dozens of similar events, revealing whether GRB 200826 was a cosmic fluke or part of a hidden population. Every outlier like this challenges textbooks, reminding us that the universe's most violent explosions still hold surprises, especially when they're over before we even finish taking notes. Among the countless flashes that have lit up the cosmos, one stands apart: GRB 090429b, a gamma-ray burst so ancient its light began traveling toward us when the universe was a mere 500 million years old, barely out of infancy. With a redshift of approximately 9.4, this burst catapults us back to an era astronomers call cosmic dawn. A time when the first stars and galaxies were just beginning to pierce the darkness of the early universe. Detecting such an event is like finding a fossilized whisper from the universe's first chapter, a remnant of conditions so extreme they defy modern simulation. What makes GRB 090429b exceptional isn't just its age, it's the pristine snapshot it offers of a universe in transition. Back then, space was a fog of neutral hydrogen, a relic of the Big Bang that hadn't yet been cleared by the ultraviolet radiation of early stars. Gamma rays, however, slice through this fog like a knife, allowing us to study epochs otherwise obscured from view. When astronomers measured the burst's afterglow, they found spectral lines indicating absorption by this primordial hydrogen, giving us direct evidence of the universe's chemical state before heavier elements became widespread. It's a time capsule from an era before planets, before galaxies as we know them, even before most of the elements that make up our bodies existed. The burst's extreme distance also challenges theories about how quickly celestial objects could form after the Big Bang. For a gamma-ray burst to occur, a massive star must live, die, and collapse into a black hole, a process thought to take at least several 100 million years. GRB 090429b suggests some stars grew to enormous sizes and burned out astonishingly fast, like matches flaring and extinguishing in cosmic seconds. These early stellar titans, known as population Roman III stars, were likely hundreds of times more massive than our Sun, composed purely of hydrogen and helium, and destined for explosive deaths that seeded the universe with its first heavy elements. But here's where the mystery deepens. The afterglow of GRB 090429b was unusually faint in optical light, hinting that its host galaxy, if it even had one, was incredibly primitive, possibly little more than a cluster of these first-generation stars. Unlike later bursts which occur in galaxies rich with dust and heavy elements, this explosion might have erupted in a near-empty void, its light traveling billions of years just to whisper its story to us. The discovery of such distant bursts isn't just about breaking records, it's about testing the limits of our cosmic models. Every detection like this one pushes the boundaries of how early stars could ignite, how quickly black holes could form, and how the universe evolved from darkness to light. With upcoming telescopes like the James Webb Space Telescope poised to study these epochs in unprecedented detail, GRB 090429b might soon have company, a growing roster of cosmic lighthouses guiding us through the universe's murky beginnings. For now, it stands as a lonely beacon from a time when everything we know was just beginning to take shape. A reminder that even the universe's most violent explosions can illuminate its deepest secrets. Catching a gamma-ray burst from the edge of the observable universe is like trying to photograph a firefly with a camera that takes hours to focus. By the time you're ready, the moment's gone. The most distant GRBs are cosmic will-o'-the-wisps, their light stretched and dimmed by billions of years of cosmic expansion, their afterglows often vanishing before telescopes can swing into position. Consider this: when light from a burst like GRB 090429b began its journey, the universe was 100 times smaller than it is today. That light has been stretched so dramatically that what began as high-energy gamma rays often arrives as faint infrared whispers, barely distinguishable from the background glow of the cosmos itself. The race to capture these fleeting explosions hinges on two brutal realities of physics. First, the inverse square law: light fades with distance squared, meaning a burst 10 times farther away appears 100 times dimmer. Second, time dilation at cosmic scales means distant bursts often appear slower and longer than they actually were, stretching their faint signals even thinner across hours or days. Unlike nearby bursts that blaze brightly enough to trigger multiple satellites, the most distant ones frequently register as borderline detections. Their initial gamma-ray flashes so subtle they could be mistaken for instrument noise. Yet against these odds, modern astronomy has developed an arsenal of tools to hunt these cosmic phantoms. Telescopes like the James Webb Space Telescope, with its unprecedented infrared sensitivity, can now spot afterglows that would have been invisible a decade ago. The key lies in speed. Automated systems like the Gamma-Ray Burst Coordinates Network can alert observatories worldwide within seconds of a detection, allowing robotic telescopes to pivot toward the burst's location before its afterglow fades. Some of these systems are so fast they can begin observing within 20 seconds of the initial trigger, capturing details about the burst's environment before it vanishes into the darkness. What's truly remarkable is how much we've learned from the handful of ultra-distant bursts we've managed to catch. Each one is a Rosetta Stone for the early universe, offering clues about star formation rates, chemical abundances, and even the topology of spacetime itself. The afterglow spectrum of one distant burst might reveal the fingerprints of primordial gas clouds untouched by heavy elements, while another could show how light interacts with the cosmic web of dark matter spanning the universe. These aren't just explosions, they're backlights illuminating the scaffolding of the cosmos. The future promises even greater discoveries. Upcoming missions like the European Space Agency's Theseus satellite will carry instruments specifically tuned to catch the most distant and elusive bursts, while next-generation gravitational wave detectors could provide complementary signals from neutron star mergers at cosmic dawn. Every technological leap brings us closer to answering fundamental questions. How quickly did the first stars form? What triggered the epoch of reionization? Are there bursts so distant they predate the first stars entirely? The pursuit of these faint cosmic flashes isn't just about setting distance records. It's about piecing together the universe's origin story, one fleeting explosion at a time. The moment gravitational wave detectors LIGO and Virgo caught the faint ripple of neutron stars colliding in galaxy NGC 4993, the entire field of astronomy transformed forever. This event, catalogued as GW170817, wasn't just a breakthrough, it was the dawn of multi-messenger astronomy, where cosmic signals arrive not just as light, but as ripples in spacetime itself. And here's where gamma-ray bursts take center stage. 1.7 seconds after the gravitational waves registered, NASA, a Fermi satellite, spotted a short gamma-ray burst, GRB 170817A, flashing from the same patch of sky. For the first time, humanity had witnessed a single cataclysmic event through two entirely different cosmic messengers, one whispering through spacetime, the other screaming across the electromagnetic spectrum. What made this detection so revolutionary was how it confirmed decades of theory. Astrophysicists had long suspected that short gamma-ray bursts arose from neutron star mergers, but GW 170817 provided irrefutable proof. The gravitational waves revealed the spiraling dance of two ultra-dense stellar corpses in their final milliseconds, while the gamma-ray burst captured the apocalyptic aftermath. The moment their collision birthed a black hole and launched relativistic jets into the void. But the surprises didn't stop there. Over days and weeks, telescopes worldwide documented the explosion's evolving glow across X-ray, ultraviolet, optical, infrared, and radio wavelengths, painting the most complete picture of a neutron star merger ever seen. This event didn't just solve one mystery, it unlocked several. The afterglow spectrum contained unmistakable signatures of heavy elements like gold, platinum, and uranium, proving neutron star collisions are cosmic forges for the universe's rarest metals. Meanwhile, the gravitational waves themselves carried subtle clues about the star's internal structure, revealing how matter behaves under pressures so extreme that atomic nuclei dissolve into a soup of quarks. Scientists even used the slight delay between the gravitational waves and gamma rays to test Einstein's theory of relativity with unprecedented precision, confirming that light and gravity travel at the same speed, 2 within 1 part in a quadrillion. The legacy of GW 170817 extends far beyond a single discovery. It marked the beginning of a new era where gravitational wave detectors and traditional telescopes work in tandem, like cosmic detectives combining fingerprints and DNA evidence. Since then, multiple neutron star mergers have been caught in this dual snare, each one refining our understanding of how these events shape the universe. Some produce gamma-ray bursts, others, curiously, don't, hinting at hidden diversity in how neutron stars collide. Some unleash kilonovae brighter than predicted, suggesting mergers might be even more efficient at creating heavy elements than we thought. Perhaps most exciting is what this synergy promises for the future. Next-generation gravitational wave observatories like the planned LISA space antenna could detect mergers at far greater distances, while gamma-ray satellites like SVOM will hone in on their electromagnetic counterparts. Together, they'll explore questions that were pure fantasy a decade ago. How often do neutron stars merge in cosmic history? Can some collisions produce magnetars instead of black holes? Could these events be responsible for unexplained flashes of high-energy neutrinos? Every coordinated detection pulls back another layer of the cosmic curtain, revealing how the universe's most violent symphonies are composed not just of light but of space-time itself. GW170817 didn't just link gamma-ray bursts to gravitational waves. It showed us the universe in stereo, where the same event can be heard and seen in perfect harmony. That convergence of sight and sound, of space-time tremors and celestial fireworks, is rewriting astrophysics in real time. And as our detectors grow more sensitive, we're tuning into a cosmos far more dynamic and interconnected than we ever imagined. Even the most brilliant gamma-ray bursts can hide their light, sometimes literally. Astronomers occasionally stumble upon mysterious, orphan afterglows, glowing remnants of cosmic explosions that appear without any initial gamma-ray flash. It's like finding the smoldering wreckage of a fireworks display but missing the moment it lit up the sky. These enigmatic events challenge our understanding of how GRBs propagate through space, suggesting some explosions fire their energy in narrow beams that miss Earth entirely, leaving behind only faint afterglows as clues to their existence. The key to this puzzle lies in the geometry of gamma-ray bursts. Traditional models describe GRB jets as tightly focused cones, like lighthouse beams cutting through the darkness. If one of these beams happens to point directly at us, we witness the full onslaught of gamma rays followed by a bright afterglow. But when the jet is angled away, even by a few degrees, the high-energy gamma rays sail harmlessly past, while the wider, slower-moving material ejected during the explosion eventually spreads out enough to become visible as an afterglow. These off-axis events give astronomers a rare opportunity to study the structure of GRB jets from an oblique angle, revealing details about their opening angles, energy distribution, and how they interact with surrounding gas. One of the most compelling examples of an orphan afterglow appeared in 2006, when the Swift satellite detected an unusual X-ray glow with no preceding gamma-ray signal. Follow-up observations revealed it was moving at relativistic speeds, matching the profile of a gamma-ray burst jet seen from the side. Further analysis showed its light curve decayed in a pattern unique to off-axis GRBs, like watching a car's taillights fade as it drives away. Similar events have since been spotted in radio and optical surveys, often lurking unnoticed until sophisticated algorithms comb through archival data to connect these fading embers to their explosive origins. Orphan afterglows don't just fill in missing pieces of the GRB puzzle, they force us to reconsider how many bursts we might be missing. Current estimates suggest for every gamma-ray burst we detect, there could be dozens more pointing in other directions, their gamma rays forever lost to the void. This hidden population implies the universe might be far more violent than our telescopes suggest, with stellar explosions happening at rates we've barely begun to measure. The hunt for these cosmic ghosts has become a new frontier in time-domain astronomy. Projects like the Zwicky Transient Facility scan the skies nightly for mysterious flashes that could be orphan afterglows in disguise, while radio telescopes like the Carl G. Jansky Very Large Array listen for the faint whispers of these events long after other wavelengths fade. Each discovery helps map the invisible geometry of GRB jets, turning what was once theoretical into something tangible. The next time you look up at the night sky, remember some of the universe's most powerful explosions might be happening just out of view, their stories written not in gamma rays but in the lingering glow they leave behind. Gamma-ray bursts might seem like chaotic cosmic explosions, but astronomers have begun harnessing their raw power as precision measuring tools, turning these violent events into cosmic yardsticks known as standard candles. The idea builds on a technique perfected with supernova, where consistent peak brightness allows scientists to calculate distances across the universe. But GRBs offer something even more tantalizing. Their mind-blowing luminosity makes them visible from the farthest reaches of space, potentially mapping regions too distant for supernova to illuminate. The challenge lies in taming their wild nature. Unlike Type Ia supernova, which explode with remarkably uniform brightness, gamma-ray bursts vary wildly in energy output, some outshining galaxies by 1,000 times, others fading into obscurity within milliseconds. This unpredictability stems from their diverse origins, collapsing massive stars, neutron star mergers, and possibly even exotic phenomena like magnetoflares. To turn GRBs into reliable distance markers, scientists must identify consistent patterns hidden within the chaos. One breakthrough came when researchers noticed correlations between a burst's peak energy and its total emitted energy, a relationship that holds true whether the GRB originates from nearby or the edge of the observable universe. Refining these correlations required sifting through decades of data. By analyzing thousands of bursts, teams discovered that certain properties, like the time it takes for the afterglow to fade by half, could serve as rough proxies for distance. The Swift satellite proved instrumental here, providing uniform measurements of bursts across vast cosmic distances. When calibrated against known redshifts from host galaxies, these patterns began forming a GRB Hubble diagram, plotting their apparent brightness against cosmic expansion. Early results are promising, with some studies using GRBs to measure the universe's expansion rate independently of supernova, offering a crucial cross-check for cosmological models. Yet obstacles remain. The sheer diversity of GRB jets, some pencil-thin, others wide-fanning, means two bursts with identical intrinsic energy can appear vastly different if viewed from different angles. New methods are emerging to account for this, like measuring the polarization of afterglow light to estimate jet orientations. Other approaches focus on rare, golden bursts with exceptionally clean afterglows whose light curves follow textbook-perfect decay patterns. These become Rosetta Stones for the entire population, helping decode the messier signals of their kin. The ultimate goal, a cosmic distance ladder that stretches further than ever before. While supernova have mapped expansion out to about 10 billion light-years, GRBs could potentially push that boundary to within 1 billion years of the Big Bang. Already, bursts like GRB 080319b with its redshift of 6.7 have demonstrated this potential, probing eras when dark energy's influence on cosmic expansion was just beginning to take hold. Future missions like the European Space Agency's Theseus aim to catalog hundreds of high redshift bursts, weaving them into a three-dimensional map of the universe's structure and growth. What makes GRBs uniquely valuable isn't just their reach, it's their ability to cross-verify other cosmic measurements. When combined with gravitational wave detections of neutron star mergers, they offer a multi-messenger approach to nailing down the Hubble constant, currently disputed between supernova and cosmic microwave background measurements. Each burst that flashes across the cosmos carries not just the story of its own violent birth, but the potential to measure the very fabric of space-time. As calibration improves, these cosmic explosions may yet become the gold standard for charting the universe's expansion, one catastrophic detonation at a time. At the heart of nearly every galaxy lurks a monster, a supermassive black hole with gravity so strong it bends the fabric of space itself. While these cosmic behemoths aren't the direct producers of gamma-ray bursts, their influence might weave into the GRB story in ways we're only beginning to understand. Picture a star wandering too close to one of these gravitational giants. In a heartbeat, the black hole's tidal forces stretch the star like taffy, pulling it apart in a cataclysmic event astronomers call a tidal disruption event, or TD. These violent encounters don't just shred stars, they can launch jets of material at near light speed, creating flares that echo the behavior of gamma-ray bursts on a smaller scale. The connection becomes even more intriguing when we consider active galactic nuclei, supermassive black holes feeding on vast amounts of gas and dust. Some of these AGN produce relativistic jets strikingly similar to those seen in GRBs, though scaled up to galactic proportions. While their timescales differ, AGN jets persist for millennia, while GRB jets fade in minutes. The underlying physics shares eerie parallels. Both involve magnetic fields twisting near black holes, accelerating particles to extreme energies. Could there be a hidden population of super GRBs triggered by supermassive black holes under rare conditions? Theoretically, yes, if a black hole's accretion disk fragments or captures an unusually massive star, it might generate a burst dwarfing even typical long GRBs in energy. Evidence for this idea surfaced in 2019 when astronomers observed a TD named at 2019 DSG. Not only did it tear apart a star, but it also launched a jet that emitted high-energy gamma rays detectable across the cosmos. This marked the first clear link between tidal disruptions and GRB-like phenomena. The jet's properties, its narrow collimation, relativistic speed, and gamma-ray output mirrored those of classical GRBs, suggesting the same basic mechanisms might operate across wildly different scales. Supermassive black holes may not produce traditional gamma-ray bursts, but they clearly possess the machinery to mimic them under the right circumstances. The most tantalizing possibility that some ultra-long GRBs, events lasting hours instead of minutes, might originate from supermassive black holes rather than collapsing stars. These marathon bursts defy standard classification, with energy outputs and durations that strain traditional models. One hypothesis suggests they could arise from rare, engine-fed scenarios where a black hole's sustained feeding, perhaps from a whole cluster of disrupted stars, powers a jet for unprecedented lengths of time. While conclusive proof remains elusive, the theoretical groundwork hints at a hidden diversity in GRB sources we've only scratched the surface of understanding. What ties these threads together is the universal language of extreme physics, whether around a stellar mass black hole born from a collapsing star or a supermassive one tearing galaxies apart. The dance of gravity, magnetism, and plasma follows similar rules. Each new discovery blurs the lines between these phenomena, revealing a cosmos more interconnected than we ever imagined. The next time you hear about a gamma-ray burst, remember, its distant cousin might be lurking in the heart of a galaxy far away, waiting for the perfect moment to unleash a light show that rivals the birth of black holes themselves. Gamma-ray bursts do more than just dazzle us with their brilliance. They pierce through the cosmic veil, revealing an era when the universe itself was undergoing a radical transformation. This pivotal moment, known as the reionization epoch, marks the time when the first stars and galaxies burned away the primordial hydrogen fog that filled space, turning it from an opaque soup into the transparent universe we know today. Studying this transition has long been a challenge, as the very gas that was being ionized also absorbed the light from those early stars, leaving astronomers with few direct observations. But gamma-ray bursts, especially the most distant ones, serve as cosmic flashlights, cutting through that ancient fog and offering a rare glimpse into this formative chapter of cosmic history. The key lies in the afterglow of these distant bursts. As the light from a GRB travels billions of light years to reach us, it passes through clouds of hydrogen gas that imprint telltale absorption lines on its spectrum. These lines act like barcodes, encoding information about the state of the gas, whether it's neutral or ionized, dense or diffuse. When astronomers examine the afterglow of a burst like GRB 090429b, with its staggering redshift of 9.4, they're effectively looking back to a time when the universe was just emerging from its dark ages. The absorption lines in its spectrum reveal pockets of neutral hydrogen, remnants of the pristine gas that hadn't yet been blasted apart by the ultraviolet radiation of the first stars. What makes GRBs uniquely suited for this detective work is their sheer power. Unlike quasars, another common tool for probing the early universe, gamma-ray bursts can be detected from much greater distances, and their afterglows provide cleaner, less contaminated spectra. Quasars, powered by supermassive black holes, often reside in galaxies rich with heavy elements and dust, which can muddy the hydrogen signatures. GRB, on the other hand, often explode in simpler, more primordial environments, offering a clearer view of the intergalactic medium as it existed before heavy elements became widespread. One of the most striking insights from these observations is just how patchy and uneven reionization was. The absorption lines in GRB afterglows show a mix of completely neutral hydrogen and regions already ionized by early starlight, suggesting this cosmic metamorphosis didn't happen all at once. Instead, it unfolded in fits and starts, with bubbles of ionized gas growing around clusters of the first stars and galaxies, gradually merging until the entire universe was clear. Some bursts even hint at a second wave of reionization, possibly driven by the rise of dwarf galaxies that contributed their own ultraviolet glow long after the first giants had faded. But the real breakthrough comes from comparing GRBs at different distances. A burst from redshift 6 might show a spectrum where most hydrogen is already ionized, while one from redshift 9 reveals a universe still largely shrouded in fog. By mapping these transitions, astronomers can piece together a timeline of reionization, not as a smooth curve, but as a dynamic, chaotic process that varied wildly from one region of space to another. It's like reconstructing a puzzle where each gamma-ray burst adds another piece, filling in gaps that other probes simply can't reach. The implications stretch far beyond understanding the universe's teenage years. These observations also test our models of how the first stars formed and how quickly galaxies assembled. If GRBs existed just 500 million years after the Big Bang, that means massive stars and the black holes they left behind were already shaping the cosmos far earlier than some theories predicted. Each distant burst forces us to rethink just how fast the universe went from darkness to light, and how the first sparks of starlight ignited the grand structures we see today. The next generation of telescopes, like the James Webb Space Telescope, is poised to take this research even further. By combining GRB afterglows with deep infrared imaging, astronomers hope to directly observe the galaxies that hosted these explosions, revealing the environments where the first stars lived and died. It's a reminder that gamma-ray bursts aren't just cosmic disasters, they're messengers from an era when the universe itself was being forged, one brilliant flash at a time. Some gamma-ray bursts refuse to fade quietly into the cosmic night instead. They stage dramatic comebacks, flaring back to life weeks or even months after their initial explosion. Astronomers call these events Lazarus GRB, named after the biblical figure who rose from the dead, and they represent one of the most perplexing puzzles in high-energy astrophysics. Take GRB 100814a, a burst that initially behaved like any other long GRB, flaring brightly in gamma rays before fading predictably in X-rays and visible light. But then, 32 days later, something extraordinary happened. Its afterglow abruptly rebrightened by a factor of 10, as if a cosmic switch had been flipped, pouring fresh energy into what should have been a dying ember. What could possibly resurrect a gamma-ray burst's afterglow so long after the explosion? One leading theory points to delayed energy injection. Imagine a black hole or magnetar at the burst's core, momentarily dormant, suddenly reactivating to pump new energy into the surrounding debris. This could happen if the central engine, instead of shutting down cleanly, experiences a secondary instability, like a final belch of material falling into the black hole or a magnetar's magnetic field suddenly reconfiguring. The revived afterglow of GRB 100814 showed spectral fingerprints suggesting exactly this, a late-stage surge of energy re-energizing the jet shockwaves like pouring gasoline on a fading campfire. But there's another, even more dramatic possibility: shock interactions with previously ejected material. Massive stars destined to become long GRBs often shed shells of gas in their final centuries, creating dense circumstellar environments. When the GRB's relativistic jet eventually plows into these distant shells, the collision can trigger a secondary outburst visible across multiple wavelengths. This scenario paints these bursts not as single explosions, but as multi-act tragedies where the initial blast is just the opening scene, followed by delayed fireworks as the shockwave encounters obstacles light years away from the progenitor star. Observations of GRBs like 060729 support this idea, with afterglows showing distinct rebrightening bumps aligning perfectly with theoretical predictions for such collisions. The real intrigue lies in what these Lazarus events reveal about stellar death throes. Their existence suggests some dying stars don't just explode, they convulse, leaving behind chaotic environments where delayed echoes of their demise reverberate long after the main event. For astronomers, these rebrightenings are golden opportunities, effectively extending the observable lifespan of a burst from hours to months, allowing unprecedented scrutiny of jet dynamics, energetics, and their surroundings. Each unexpected flare peels back another layer of mystery, proving that even the universe's most violent explosions can still surprise us with second acts. Gamma-ray bursts don't just shine in gamma rays, they paint the cosmos across the entire electromagnetic spectrum, from radio whispers to the highest energy gamma rays ever recorded. Take GRB 190114C, a burst so powerful it flooded space with photons packing trillions of times the energy of visible light. When the magic telescopes in the Canary Islands detected this very high-energy gamma-ray flash in 2019, it shattered expectations. These weren't the typical gamma rays we're used to seeing from bursts. They clocked in at tera-electron-volt energies, a realm where particles behave more like cosmic bullets than light waves. The discovery forced scientists to rethink how these jets accelerate particles, suggesting shocks within the jet itself might be acting as natural particle colliders far more powerful than anything on Earth. But the real magic happens when we piece together observations from multiple wavelengths. Radio telescopes like the Very Large Array often catch GRB afterglows weeks or months after the explosion, revealing how the jets interact with their surroundings at microscopic detail. These radio echoes can linger long after other wavelengths fade, mapping the deceleration of shockwaves as they plow into interstellar gas. Meanwhile, infrared observatories like the James Webb Space Telescope peer through cosmic dust, uncovering bursts hidden from optical telescopes. In some cases, infrared afterglows reveal clues about the host galaxy's composition, like how much dust has been cooked up by previous generations of stars. Perhaps the most unexpected revelations come from combining these observations. A burst might appear unremarkable in gamma rays but erupt with startling radio brightness, hinting at a dense environment sculpted by the progenitor star's winds. Others, like GRB 190829A, flared in high-energy gamma rays while remaining mysteriously quiet in visible light, a mismatch that led astronomers to suspect they were seeing the jet from an oblique angle, like catching a lighthouse beam from the side. Each wavelength adds a new dimension to the story. X-rays probe the innermost workings of the central engine, optical light traces intermediate-scale shocks, and radio waves chronicle the jet's long-term marriage with its surroundings. Together, they transform gamma-ray bursts from one-dimensional flashes into rich cosmic ecosystems, where every frequency band reveals another layer of physics at work. The next time you hear about a gamma-ray burst, remember, it's not just a flash in the dark, it's a symphony of light playing across every instrument in astronomy's orchestra. The future of gamma-ray burst astronomy is brighter than the explosions themselves, thanks to a new generation of telescopes poised to rewrite the textbooks. Leading the charge is the Vera Rubin Observatory, currently taking shape atop Chile's Cerro Pachón. With its revolutionary 8.4-meter mirror and a camera the size of a small car, Rubin will scan the entire southern sky every 3 nights, an unprecedented feat that could spot dozens of faint, distant GRB afterglows other telescopes would miss. Unlike current missions that rely on gamma-ray triggers, Rubin's sheer volume, capturing over 20 terabytes of data nightly, will let it catch orphan afterglows and rare late-time rebrightenings purely by their optical signatures. It's like trading a single flashlight for a stadium's worth of floodlights, illuminating cosmic explosions hiding in plain sight. Meanwhile, the European Space Agency's Athena mission, slated for launch in the mid-2030s, will peer deeper into GRB physics than ever before. Armed with an X-ray calorimeter so precise it can measure the energy of individual photons, Athena will dissect afterglows with surgical precision, tracing how jets dissipate energy across millennia. One of its key targets, the elusive, missing population of ultra-distant bursts, those originating within the universe's first few 100 million years, whose light has been stretched into oblivion by cosmic expansion. Athena's sensitivity could spot bursts at redshifts beyond 12, probing an era when the first stars were just flickering to life. But the real game changer might be the synergy between these instruments. Imagine Rubin flagging a candidate orphan afterglow, only for Athena to swoop in with high-resolution X-ray spectroscopy, revealing the burst's elemental composition and the density of its surroundings. Or consider the potential of combining Rubin's wide-field alerts with the James Webb Space Telescope's infrared eyes, allowing us to study the host galaxies of primordial bursts in unprecedented detail. Together, these observatories could solve long-standing mysteries. Are there bursts from population Roman 3 stars, the universe's first stellar generation, that lack heavy elements entirely? Do some GRBs originate from black holes born from dark matter annihilation? The answers may lie just beyond our current detection thresholds. On the horizon, even more ambitious projects loom. The Einstein probe, set to launch in 2024, will monitor the X-ray sky for GRB counterparts with lobster eye optics inspired by nature's design. Further out, concepts like the transient high-energy sky and early universe surveyor Theseus promise to extend our reach to redshifts of 15 or higher bursts so ancient they predate most galaxies. These missions won't just find more GRBs, they'll test fundamental physics, from the behavior of matter in extreme magnetic fields to potential variations in the speed of light across cosmic time. What's truly exhilarating is how these tools might reveal surprises we can't yet predict. Before Swift launched in 2004, no one imagined it would discover ultra-long GRBs lasting hours or catch black holes hiccuping material long after their initial explosion. Similarly, Rubin and Athena could uncover entirely new classes of transient events linked to GRBs, perhaps bursts from quark-star mergers or primordial black hole collisions. Every technological leap in astronomy has rewritten the cosmic playbook, and this next chapter promises to be the most revealing yet. One thing's certain, the golden age of gamma-ray burst science isn't behind us, it's just beginning. Gamma-ray bursts might seem like fleeting cosmic fireworks, but their cumulative impact could shape the universe's destiny over billions of years. Think of them as celestial sculptors, their explosive energy carving voids in interstellar gas and influencing where and when new stars can form. In the early universe, when galaxies were smaller and GRBs more frequent, these explosions might have acted as cosmic regulators, blowing away the raw materials for star formation in some regions while triggering collapse in others. The aftermath of a single burst can heat surrounding gas to millions of degrees, creating bubbles so vast they persist for cosmic epochs, effectively sterilizing entire swaths of a galaxy from future stellar births. But here's where it gets even more intriguing. Some theories suggest GRBs could have played a role in one of the universe's greatest mysteries, why star formation peaked around 10 billion years ago and has been declining ever since. Picture the early cosmos, galaxies brimming with dense gas, birthing stars at a furious pace. Massive stars lived fast, died young, and often ended as GRBs, their explosions injecting energy back into their surroundings. Over time, this feedback loop, explosions heating gas, preventing it from cooling and forming new stars, could have gradually throttled galaxy-wide star formation, like a cosmic thermostat turning down the heat. Observations of distant galaxies hosting GRBs often show depressed star formation rates, hinting at this delicate balance between creation and destruction. The most dramatic scenarios propose GRBs as key players in cosmic reionization, the epoch when ultraviolet light split neutral hydrogen atoms apart, rendering the universe transparent. While the first stars and quasars are often credited with this transformation, GRBs may have contributed significantly, their intense radiation punching through hydrogen fog more effectively than starlight alone. Each burst's high-energy photons could ionize gas thousands of light-years beyond its host galaxy, creating overlapping bubbles of transparency that eventually merged. This might explain why reionization was so patchy, with some regions clearing earlier than others. GRB, being rare and randomly distributed, would have lit up the cosmos in fits and starts rather than a smooth wave. Yet GRBs aren't just destroyers, they're also unlikely enablers. The heavy elements forged in their explosions, gold, uranium, even the calcium in your bones, seed future generations of stars and planets. Without these periodic cataclysms, galaxies might lack the metals needed to form Earth-like worlds or the chemistry for life itself. It's a paradoxical dance. The same explosions that suppress star formation in one era enrich the universe with the building blocks for complexity in the next. Future telescopes like the European Space Agency's Ariel mission could test this by studying metal-rich exoplanets in galaxies with different GRB rates, searching for patterns linking these bursts to the prevalence of habitable worlds. The ultimate legacy of gamma-ray bursts might be written in the large-scale structure of the cosmos. Simulations show that their energy input could subtly alter how galaxies cluster along filaments of dark matter, influencing the cosmic web itself. While individual bursts are fleeting, their collective imprint over billions of years may be etched into the distribution of galaxies we see today. As astronomers map the universe in ever greater detail, they're searching for these faint signatures, evidence that the universe's most violent explosions quietly shaped everything from the smallest planets to the grandest superclusters. Far from being mere cosmic oddities, GRBs could be silent architects of the universe's evolution, their fingerprints hidden in plain sight. Astronomers face a cosmic head-scratcher when it comes to gamma-ray bursts in the early universe. The numbers just don't add up. Based on our understanding of star formation rates in the ancient cosmos, we should be drowning in distant GRBs, with telescopes spotting them at redshifts of 10 or higher on a regular basis. Yet the reality is starkly different. The record holder, GRB 090429b, sits at redshift 9.4, and beyond that, silence. This glaring gap between prediction and observation has become one of modern astrophysics' most nagging mysteries, dubbed the missing GRB problem. One compelling explanation points to metallicity, the cosmic abundance of elements heavier than hydrogen and helium. In today's universe, massive stars rich in metals tend to lose their outer layers through powerful stellar winds long before collapse, leaving less material to fuel the ultra-relativistic jets needed for GRBs. But in the early universe, where metals were scarce, stars could theoretically retain their bulk, creating ideal conditions for powerful bursts. The twist. Recent simulations suggest the first star's population, Roman 3, might have been too massive and unstable to produce traditional GRBs at all. Instead of collapsing into neat jets, these behemoths may have exploded entirely or imploded directly into black holes without the telltale gamma-ray fireworks. This creates a paradoxical Goldilocks zone for GRB formation: too early and stars are too primitive, too late and they're too metal-rich. Observational biases add another layer of complexity. Detecting ultra-distant GRBs requires catching their afterglows in infrared wavelengths, as cosmic expansion stretches their light far beyond the visible spectrum. Current satellites like Swift and Fermi excel at spotting gamma rays but often miss the faint, redshifted afterglows crucial for confirming high-Z events. It's like trying to spot a firefly in a foggy forest. You might hear its wings, the gamma-ray flash, but lose sight of its glow before identifying it. Compounding this, the James Webb Space Telescope's limited field of view means it can't routinely scan for afterglows unless other instruments first pinpoint their locations. The plot thickens when considering burst duration. Long GRBs linked to massive star deaths dominate the high redshift record, but their progenitors may have been rarer than we assumed in the early universe. Some models propose that the first galaxies were so small and isolated that stars massive enough to produce GRBs formed only in exceptional circumstances. Meanwhile, short GRBs from neutron star mergers would take billions of years to occur, far too long to show up in the universe's first few 100 million years. Yet hope isn't lost. Upcoming missions like the European Space Agency's Theseus satellite, designed specifically to hunt high redshift GRBs, could rewrite the story. With infrared-sensitive instruments and rapid response capabilities, it may finally reveal whether the missing bursts are truly absent, or just hiding in wavelengths we've been blind to. Every theoretical model hangs in the balance, waiting for that one flash from the cosmic dawn to illuminate whether our predictions are flawed or our tools simply haven't been sharp enough. The answer could redefine not just GRB science, but our entire understanding of how the first stars lived and died. In October 2022, the cosmos unleashed an explosion so bright it temporarily blinded gamma-ray telescopes GRB 221009A, aptly nicknamed the BOAT for brightest of all time. This monstrous burst erupted from a galaxy nearly 2 billion light-years away, yet its light was so intense it saturated detectors on NASA, Fermi, and Swift satellites, forcing astronomers to piece together its true energy from fragments of overexposed data. Initial estimates suggested it unleashed photons with a combined energy of 18 teraelectronvolts, equivalent to the kinetic energy of a baseball hurtling at 60 miles per hour but packed into subatomic particles. For 70 hours afterward, its X-ray afterglow outshone every other source in the sky, including our own sun, casting a shadow over routine observations like a cosmic spotlight hijacking the heavens. What made the BOAT exceptional wasn't just its raw power, but the lingering mysteries it left in its wake. Most gamma-ray bursts follow predictable patterns. Their light curves rise, peak, and decay in ways that align with models of collapsing stars or merging neutron stars. GRB 221009 defied every template. Its gamma-ray emission lasted an unusually long 10 minutes, with erratic pulses suggesting the central black hole might have experienced multiple collapses or fed in violent spurts. Even more puzzling was its lack of an accompanying supernova. Long GRBs typically signal the death of massive stars, yet weeks of follow-up observations found no trace of the expected stellar explosion, leaving theorists to wonder, did this progenitor star collapse directly into a black hole without the usual fireworks, or was there some exotic new mechanism at play? The burst's aftermath revealed another riddle: an oddly narrow jet. High-resolution radio observations showed its outflow was just 2 degrees wide, far tighter than typical GRB jets. Normally, such a focused beam would mean we'd only detect the burst if Earth happened to lie directly in its path, making the BOAT's record-breaking brightness even more improbable. Some scientists speculate the jet might have been structured with an ultra-energetic core surrounded by weaker lobes, or that it plowed through an unusually dense patch of interstellar material, amplifying its glow through external shocks. Others propose the burst's extreme luminosity came from a perfect storm of factors: a rapidly spinning black hole, a magnetically choked accretion disk, and a progenitor star with unique properties lost to cosmic history. Perhaps the most startling revelation came months later, when astronomers realized the BOT had left a radioactive scar on Earth's upper atmosphere. Its gamma rays ionized atoms in the ionosphere, distorting very low-frequency radio signals used for submarine communications, an impact normally seen only during solar flares. This marked the first time a cosmic explosion outside our solar system was caught affecting Earth's atmosphere, a humbling reminder of how interconnected the cosmos truly is. As researchers continue sifting through the data, GRB 221009 stands as a cosmic Rosetta Stone, an event so extraordinary it challenges our understanding of stellar deaths, jet physics, and the limits of energy release in the universe. Future telescopes may eventually spot its rivals, but for now, the BOT remains in a class of its own, proving that even after decades of study, the universe still has the power to astonish us. Its legacy isn't just in shattered records, but in the questions it forces us to ask, and the certainty that somewhere another monster lurks in the dark, waiting to rewrite the rules once more. From the staggering energy of hypernova to the ghostly whispers of orphan afterglows, these 30 facts reveal gamma-ray bursts not just as cosmic disasters, but as luminous guideposts to the universe's deepest secrets. They've shown us stellar corpses spinning gold from chaos, black holes born screaming into the void, and flashes of light so ancient they predate Earth itself. Each distant burst is a time capsule carrying clues about the first stars that ignited, the hydrogen fog they burned away, and the violent adolescence of a cosmos finding its shape. Consider the raw scale of these phenomena. A single GRB can outshine galaxies, hurl particles with the energy of a speeding bullet, and leave scars on planets billions of light-years away. Yet for all their fury, they're also creators forging the heavy elements in our jewelry and smartphones, sculpting galaxies by seeding space with metals, and possibly even influencing where life could arise. The most distant bursts, like GRB 090429b, act as cosmic archaeologists' tools, letting us witness the universe as a newborn, when stars were giants and black holes were just beginning their reign. But beyond the science, gamma-ray bursts offer something humbler perspective. That flash you might see in the sky tonight, it could be the last cry of a star that died before our sun existed, its light finally reaching us after an unimaginable journey across expanding space. It's a reminder that we're spectators to events older than continents, older than oceans, older than the very atoms that make up our bodies. So what do you think? Do these explosions make you marvel at the universe's grandeur or shudder at its indifference? Have we glimpsed all there is to know about GRBs, or are the most revolutionary discoveries still hidden in the darkness? Drop your thoughts below, and let's keep unraveling the cosmos' greatest mysteries together. After all, the next record-breaking burst could flare up at any moment, and when it does, we'll be here to decode its story.